So before we jump into the specifics of quadratic equations and their graphs, I want to go over just some general concepts. So some vocabulary and some formulas that we will be talking about throughout these lessons. So everything that I highlight or circle or write in is important. I know there's a lot of words on here, but as we go into more detail on each of these bullet points, it will make more sense and we'll do more practice regarding it. Hopefully this will just be a good summary page to come back to. So our first vocab word is a parabola. So a parabola is just the U-shaped graph of a quadratic function. So on the second page, I have four parabolas. It's just a U, whether it's an upward facing U or a downward facing U. That's called a parabola. What it means by a degree of 2 is just that there's an x squared in the equation. So we don't just have an x with an exponent of 1, we also have an exponent of 2 on our variable. That's the key. And it would look like a U. So we've got an upward facing U and we have a downward facing U. A quadratic function is a function that can be written in the form f of x equals ax squared plus bx plus c, where a, b, and c are all real numbers and a cannot be 0. Notice that in this equation, b and c could potentially be 0. The number that cannot be 0 is the coefficient that is in front of our x squared, because that is what creates the quadratic function. And I'll write this. Standard form of a quadratic function is just one of the 3 ways that we can write quadratic functions, so it's what we're used to seeing so far. So the standard form is an ax squared plus bx plus c form, which is what we're used to working with. That's the format that actually all of these formulas are going to go back to. So we will be using standard form to match up these formulas later on in the sheet with whatever function we're dealing with at the time. Really quickly, we know that if a is greater than 0, then the parabola opens up. So it's gonna look like this. So when we have a positive value for a, it opens up. When it opens up, there's a minimum value. If a is less than 0, then the parabola opens down and it has a maximum. So this is when we have a positive a, and this is when we have a negative a. The x-intercepts of the graph of a quadratic function are the x-coordinates of the points at which the graph intersects the x-axis. So not all quadratic functions have x-intercepts. For example, if this is my coordinate plane and this is my parabola, notice that this has a y-intercept, but there are no x-intercepts because it never crosses the x-axis. So that's an example of when we don't have an x-intercept. There are multiple words for x-intercepts, and this is super, super important. I'm going to write it in another color. So x-intercept can be called an x-intercept. They can be called roots, and they can be called zeros. So these 3 words all mean the same thing. It's just asking where I cross the x-axis. You can find the x-intercepts by factoring, which is what we've talked about in the previous lessons. And what we haven't talked about yet is the fact that sometimes it's not easy to factor a function by hand. And in that case, you can use the quadratic formula to find the x-intercepts. So this formula just tells me what each x-intercept is. One of the times you use a plus sign here, and that'll give me one x-intercept. And then you do this formula again, and you'll use the minus sign, and that'll give you the other x-intercept. So this is our quadratic formula. We have our x-intercepts, which is this. And so our quadratic formula, and we have a song that we can learn in order to memorize it, but that's what that is. The discriminant of the quadratic equation, it's just what's under the root. So if you're thinking about the discriminant, it's just what is underneath the square root sign. That is the discriminant. If this is a negative number, then we don't have any x-intercepts because you can't take the square root of a negative number, which is what it says right here. If the discriminant is negative, then there are no x-intercepts. So we can go down. We have y-intercept of the graph of a quadratic equation is just the y-coordinate of the point at which it crosses the y-axis. That is the same as what our definition has always been. It is also the letter C in our standard form equation. The axis of symmetry of a parabola is the line through the vertex of the parabola about which the parabola is symmetric. There is a lot of words in that statement, in that definition, but what we're going to focus on right now is just thinking that we have this line of symmetry, which means it's the same on both sides, which if I have my coordinate plane and I have a parabola, so something like that, I know that there is a line down the middle, in which this case we have our maximum value, right? On the right side of it and on the left side are the exact same. They are mirror images. What this line is called is the axis of symmetry. And we can find this value by plugging in to this equation. Using standard form, we put negative, whatever our value for the coefficient of b is, all over 2a. Whatever that x value is, so pretend in this case it's -2, we go to x equals -2 and draw a line because that is our line of symmetry. So, that includes our vertex, because our vertex is just either the maximum or the minimum. A maximum gives me the greatest value. A minimum is the least y value. We know we have a maximum when the parabola opens down, which happens when we have a negative a value. We know we have a minimum when the parabola opens up, which is a positive a value. And we know that this point, whether a maximum or a minimum, we know that that is called the vertex. The vertex's x value is just the x value that you got from the line of symmetry. So if you have your line of symmetry's x value, which is just this, you're just going to plug it into your equation for standard form and solve for the y value. That's what all of this nonsense means. It's not meant to confuse you, but it does look really complex. So if you remember that when we're doing f of x, that just means you replace x with whatever's inside of the parentheses. So we're just replacing x into the equation in standard form and solve for y. Okay. And then lastly, this just kind of puts everything together. So it says that the key features of quadratic function are used to describe, draw, and compare quadratic functions. That includes the x-intercepts, the y-intercepts, the values of x for which the function is increasing and decreasing. We didn't talk about that on the other page, so we'll address that. And for which the graph of the function is positive and negative, its minimum or maximum, which we talked about, the axis of symmetry, and then the end behavior of the graph of the function. So really quickly, and hopefully this seems familiar from past units, we know that increasing and decreasing is referring to the slope. So I know, and I'll write this down at the bottom down here, that increasing versus decreasing, you are thinking about slope. So for example, on this graph, from here all the way to our vertex, it's decreasing because we have a negative slope. So this is just a positive slope. I'm just writing this down here. And a negative slope. So we know that this is decreasing. When we're thinking about positive versus negative, so if it says what part of the graph is positive and what part of the graph is negative, you're thinking about the y value. So you're thinking for which values of x is my graph positive? So for which values of x do I have positive y values? So down here, I'm just going to write a note for that. Positive versus negative. You're looking at the y values. So for example, from here all the way to here, so from x equals like negative 1.25 to x equals 3.25, from here to here, it's considered to be, the graph is negative in this range because our y values in this given domain are negative. So we call it just negative. Okay. And then last but not least, you're saying the end behavior. So for example, if you're looking from left to right, this is just increasing. The end behavior is increasing. I know that as x goes toward, as x goes toward positive infinity, y also goes to positive infinity. It's a little different if you have a parabola that opens down, because as x goes to positive infinity here, as it gets bigger and bigger and bigger, the y value is getting lower and lower and lower. So here we would say as x goes to positive infinity, y goes to negative infinity. So that's just what it's asking about when you're thinking about the end behavior of the graph.